Okay, so I'm gonna continue talking today about symmetries in parameter space for parameterized function classes for learning. So just to remind you, if F is a parameterized function class for learning, so we have in mind the class that we've been thinking about a lot, which is ReLU neural network functions. But what I'm saying is much more general. Then you can think of this as being a continuous function from the product of the parameter space and the input space to the output space. And just to remind you of notation, if theta is a parameter, I'll call F theta a function from input space to output space. So this is sort of the functions that we're thinking about for the parameterized function class. But there are also these evaluation maps, which are where you fix an input point and you allow the parameter to vary. And that's naturally a map that naturally gives a map from parameter space to output space. And we're kind of interested in both. Okay. So last time I introduced the notion of a global parameter space symmetry. So that's just an action of a group, or rather a semi-group, because we want to allow for the corresponding functions on parameter space to possibly be non-invertible. But so a global parameter space symmetry is an action of a semi-group on parameter space that fixes all functions in the parameter space. So regardless of the input point, it's a map from parameter space to itself that gives you back the same function. And I mentioned that these aren't the only kinds of parameter space symmetries that you can think about. And in fact, it's interesting to think about parameter space symmetries that are only valid locally, because there's somehow this informal belief that parameter space is somewhat inhomogeneous with respect to various notions of complexity for modern parameterized learning classes. Okay, so I won't recall the definition of local parameter space symmetry right now. Instead, I'm just going to say, so we sort of have in mind that F is a class, parameterized function class of ReLU neural network functions of a fixed architecture. And let me just give an example. So I mentioned that there's this informal belief that somehow these classes that are used in modern machine learning should be inhomogeneous in terms of complexity as you move through the class. So rather than kind of dive right into the definition that I want to focus on for today, let me give just a couple of examples to kind of convince you that this class already, it's very simple toy examples to convince you that this class you should believe is inhomogeneous. So let me find my examples here. Here we go. Okay, so let's actually, I need to get myself a little bit of space. So here's some toy examples. And this will also allow us to kind of remember a little bit about the geometry of ReLU neural networks. So I'm just going to literally take maybe the smallest example that's interesting. This is 1-2-1 architecture. So these are univariate ReLU neural network functions, one-dimensional input, one-dimensional output. So if we look at what the network would look like this. Single hidden layer, dimension 2. And we can count the dimension of parameter space here. So my upper index here is the first layer map. My lower index is, sorry, yeah, right. So the rows correspond to the outputs here. So we have 7 parameters. So this is a 7-dimensional parameter space. And let's think a little bit about what. So remember that associated to each of these layer maps, you have an affine hyperplane arrangement, which tells you the boundaries between when the various neurons are on or off. So I'm just going to kind of denote these here like this. So imagine, and I'm not going to write down parameters. I'm just going to draw some pictures. So imagine, so an affine hyperplane arrangement in dimension 1 is just a pair of points, and if it's generic, then the pair of points are different. And imagine that, so remember our affine hyperplane arrangements come with co-orientations that tell you, so this is, say, the first neuron, and this is the second neuron, so the first component, second component. And let's say that that this first neuron is on here and off here. Second neuron is on here and off here. Okay, so if you were to label this according to our ternary labeling that we've been, sorry, that's wrong. This is -1. This is 1. So this is saying that this is telling us that the first neuron is off and the second neuron is on here. Okay, and remember that what that tells us, so here I'm kind of drawing the 0 sets of these 2 neurons, the pre-activated neurons here. And now let's look at the image of this map in R2. So again, this is not exact because I haven't told you any parameters, but at least we know, roughly speaking, what the picture looks like, because the ternary labeling tells us which face of the non-negative orthant that part maps into. So this maps to the y-axis. So let me actually give things colors. I'll just leave that white. So this would look something like this. Okay. Great. And now here we are with the image of the first layer map in R2. And now to understand the second layer map, we need to, so corresponding to the second layer map is a single affine hyperplane, which is the 0 set of this neuron, along with the co-orientation. So imagine, just for the sake of argument, that whatever that is, it looks like this, and it's co-oriented this way. Okay. So now let's think about how we might represent the overall map. So we can talk about the graph of that map. And the graph is really determined somehow by the height of these points above this hyperplane. You know, it matters what the length of this vector is, what the length of the weight vector is, for example. But essentially, you know, this kind of tells us what the overall shape of the graph looks like, because everything below this gets zeroed out because it's on the wrong side of the hyperplane. And so if we look at the overall graph of the function, or sort of these pictures, well, would look something like, this, And then you have this flat part. Looks like that. And you have something coming up. And then goes up a little bit. Okay, so this is the graph of the overall function. Oh, I already wrote that. Okay, so just by inspection, what you can see is that the number of possible parameters that can parameterize functions of this kind, well, there are at most 6. And the 6 are the slope of this, where it intersects here, where it intersects here, the slope of this, where it intersects here, and the slope of this. So so there's 6 possible degrees of freedom. For functions of this kind of combinatorics, at most. So you can kind of convince yourself of that. But now imagine that instead, let me just give a slightly different setup. Imagine instead that this was pointing the other way. I guess I want both of these to be pointed this way. So then we have neither of the neurons is on here. One is on here, both are on here. So what that tells us, and again, I'm just going to sort of change everything here. What that tells us is this whole one-dimensional ray gets mapped to the origin here because both components have to be 0. Then we have this white portion here that's just going along the x-axis, and then it starts to go up into the open part of the non-negative ortho. So the image of the first layer map looks something like this. And then now if you have, for example, an affine hyperplane that looks like this, and you try to draw its graph, well, the point is that once you consider points that are coming from here, they're always going to be the same height above this hyperplane. So this part is going to be flat. And I'm just going to draw the graph of f theta in this case. So you have some kind of flat part, then it's going to come down as it gets closer to this affine hyperplane. And then it'll come down some more. And then it'll be flat again. And you can convince yourself that this has it has a lower upper bound on the number of possible degrees of freedom. So this has at most 5 degrees of freedom. Because the shape of the graph is going to basically look like this, if the combinatorics looks like this. Okay. Of course, there could be additional things that are linked, like maybe this slope depends on that slope, or this slope depends on that. So this is just an upper bound for the number of degrees of freedom, but we know for sure that the graph looks like this. So we have an upper bound.
Wait, sorry, I didn't understand why that one only has 5 degrees of freedom, because you still need 3 slopes and 3 y-intercepts.
No, let's see, you have, oh boy, okay, so this
flat lines.
Yeah, you have
Parallel
two.
lines.
Yeah, you have 2 flat lines. You have this point, that slope, And that slope, let's see. I know it's less than the other one. I might have miscounted, but
Looks like 3 points and 2 slopes, the 2 slopes in the middle.
it's 2 slopes. Yeah, and that determines the height here. Yeah, if you know this point and you know this slope, and you know this point, and you know that slope. So that's 1, 2, 3, 4. And then you have to say where you cut off, so that's 5. Okay. Anyway, point being, I'm pretty sure I did the count right, but even if I didn't, the point is that that these combinatorics do kind of determine different fundamentally different looking graphs. And so even in this very, very simple architecture, you can start to see how there might be some inhomogeneity. Okay. All right, so let me now make a definition. So let's let that be a parameterized function class. For learning. So it's also smooth away from a measure 0 set. And let's let theta naught in omega be fixed. Z be a batch of parametrically smooth points. So in particular, they're theta naught comma zi are all away from that measure 0 set of points in the product where the gradient is not well defined. So parametrically smooth, parametrically. Nice. For theta. Then the batch functional dimension. So batch for this batch. And we're thinking of this as maybe being like a batch of training points for a supervised learning problem. Functional dimension of theta naught on this batch C. So what you do is you look at each of the EZIs. So I'm going to write something down. So actually, I should have said this definition first. But okay, so we know what these EZIs are. Now what we're going to do is just going to stack them. So imagine each of these as a vector, and we're just going to write them kind of one after the other in this whole batch. This is now a m times nb, the output dimension vector of these evaluations on theta naught. And now you just take the the gradients of each of these components with respect to the parameters. So JEZ is now MND by dimension of the parameter space. Work is not great here, sorry about that. So each row here is now the gradient of BZI of theta evaluated at. So with respect to theta, evaluated at theta naught. Let me write it that way. So each one of these is now a function just of theta. And this gradient is well defined because these points are parametrically smooth. And you're taking the gradient with respect to the parameters, and then you're evaluating at theta equals theta naught. So this is now an MND by dimension of the parameter space matrix. And the batch functional dimension is the rank of this matrix. So this is kind of slightly easier to parse in the case where the output dimension is just one, because then this is just, you just have m points and you have the gradients associated to each of those. So then if you think about that's somehow an easier case to think about. And when you think about that, essentially what you're saying is you're looking at so the span of these gradient vectors are exactly the vectors in the tangent space at theta naught of parameter space that you can move when you're doing gradient descent. So this rank is the dimension of the subspace of tangent space that you can move when you're doing gradient descent on this batch of points. Okay, so let me write that down. Informally. So let's give this a name. Let's call it FDIM sub Z theta naught. So the batch functional dimension on the batch Z of theta naught. The dimension of the subspace the tangent space at theta naught of omega, the parameter space. Which one can move doing gradient descent on the batch on any empirical loss function. In particular, if there are any locally defined symmetries, then they will be orthogonal. They will be in the kernel of the sort of form that's induced by these gradient vectors. Any questions about that? I'll say more about this soon, but and also I'll make some comments. This is closely related to the neural tangent kernel. In fact, I almost think of this as being the neural tangent kernel in a certain sense. People define the neural tangent kernel differently. I mean, they actually define it as the actual inner product on tangent space. But what people mean when they talk about kernels and kernel learning is really some kind of map from your input space to some Hilbert space. So some space that has an inner product on it. And in this case, for the neural tangent kernel, that map is the map into the tangent space that I just told you. Okay, so when people talk about when people talk about the neural tangent kernel, that's really what they're talking about. I think. They might say it differently, but I think that's what they're talking about. So I'll say more about kernels later, not today. I'm kind of not ready today to talk about kernels, but I'll at least make the remark that I just said. So this is essentially the representation from R0 to a Hilbert space. In this case, the Hilbert space is the tangent space at a particular parameter. Jacobian is essentially that. And the rank is measuring something about that kernel. It's measuring the rank of the kernel. Well, the rank of the corresponding inner products, pairwise inner products. That the positive semi-definite form that you get by taking that the Jacobian and multiplying it by its transpose. Okay, I'll say more about that later when I'm kind of more prepared to do that. But for now, let me see, what do I want to say? Right. Let me show you some thoughts, actually. That's the first thing I wanted to do. So I'm gonna. So I claimed that it's claimed that functional dimension. Oh, I didn't quite define the functional dimension. I just defined batch functional dimension. But for functional dimension, you just take the supremum over all batches of finitely many points. So somehow what you're trying to capture is what the sort of maximum possible dimension of a subspace of tangent space is that you can get at when you're doing gradient descent near that point. So in other words, you're looking at the possible ways in which you can perturb your function locally so that you can change you can change the function itself at all locally. Okay, so let me show you these plots. Okay, to get rid of this. Shoot, that thing. Smaller. Do that. Nope. Why am I struggling to get this out of the way? Okay, let me just do that. Okay, so essentially what I'm trying to convince you of is that so these are some experiments that our collaborator David Rolnick did. Basically doing a lot of runs and computing this batch functional dimension for a large number of points. So we call this the approximate functional dimension because we don't actually know that it's this true supremum. And in fact, it's really hard to get at that true supremum. So we have some results about how to sample the points so that you can actually, you can achieve the supremum of this or the max of this batch functional dimension. But what we but it's actually very computationally intensive to figure out. So essentially what you need is that you actually need the decomposition of your domain into this polyhedral complex so that you can sample points from each of the top dimensional cells of this polyhedral complex. And that's hard to do. But you can try to get at it by just taking a bunch of points. Of course, what you're not capturing here is whether or not there's any kind of bias in terms of how those points would land in the various regions of your polyhedral decomposition. But we kind of just sweep that under the rug by calling it approximate. So we don't know that this is the functional dimension, but you can see that there's kind of a spread. So for very shallow networks, so this is kind of the most that the functional dimension can be. And I'll explain that momentarily. But you see that as the network gets deeper, the spread gets bigger. So that's kind of an interesting effect that I'll also try to explain a little bit later. Or at least some hints about why that might be a little bit later. But this is mostly to convince you empirically that that functional dimension is actually inhomogeneous. Okay. Just stop this. So maybe let me prove one thing, or at least kind of sketch the proof of one thing. So here's a theorem. So this appeared in our paper with Catherine and Rob Meyerhoff and Chen-Chi Wu, where we define the functional dimension. But I suspect it's in the literature somewhere, maybe before this. So, yeah, for all of these architectures, and for all theta naught. So I defined these terms before, but I'll just kind of remind you what they mean, roughly speaking. So, generic and super transversal for a parameter just means about the polyhedral complex, that the dimension of a cell in the polyhedral complex corresponds to the number of zeros the codimension of a cell in the polyhedral complex corresponds to the number of zeros in the ternary labeling for that cell. So, yeah, basically, if you have a top dimensional cell, then it's kind of in the sign pattern for all of the neurons is what you expect. It's plus and minus ones. And if you see a zero, it's because you're actually on a bent hyperplane in your bent hyperplane arrangement. Okay, so that's what generic and super transversal means. And the functional dimension, again, remember this is the supremum over all batches, is less than or equal to this is the parametric dimension. Minus the number of hidden neurons. And the sort of sketch of the proof is to look at the space of known global symmetries. So consider the space of known global symmetries. On omega. So this is for F class of Rowley networks of architecture. So we talked about this last time. So remember what you have, if you're a linear network, then you have an action of GLN1 cross ... through GLN D minus 1 by conjugation at each hidden layer. Okay, so recall we let P, let's call it PL, be the space of so it's the subgroup of the general linear group, NL by NL matrices, which are diagonal matrices with positive entries. Then what we see is that P1 cross P and D minus 1. So there's a map into C infinity, so smooth maps of parameter space onto itself by conjugation. Each hidden layer. in the way that we were describing last time. So each of these positive diagonal matrices induces a map. And if you look at the derivative of this map on the tangent space, then it's a linear action on the tangent space. Um, Goofy. And you can convince yourself that this linear map. So the claim is that so if you say pick a particular positive diagonal matrix P1 through P minus 1. It's going to be in the kernel of, it's going to have zero dot product with any gradient. Be orthogonal to any gradient. In these gradients. So the point is that these gradients are spanning some subspace of the tangent space. And you have this collection of derivatives of these smooth representations, or these representations of this linear group into smooth maps on your parameter space. And these will all be orthogonal to these gradients. So if you can convince yourself that their span is at least, well, it's not hard to convince yourself that say one of these maps, say with one on the diagonal, everywhere except for a single, say 2 somewhere, that all of those will be linearly independent from each other. And so you have exactly number of hidden neurons, ones of those. So, by showing that there are the span of is at least well, is equal to. Then the conclusion follows. So again, I'm just sketching this, but it's actually not hard to fill in the details here. You just have to pick particular, you have to pick particular matrices here that are obviously linearly, whose derivatives are obviously linearly independent in tangent space. And I kind of told you which ones to pick. Say, one's on the diagonal everywhere except for a single 2 somewhere. And those will be linearly independent. It doesn't have to be 2, just something that's not 1. Okay. So the point is that these are directions for which the function doesn't change. So modding out by those directions, the possible rank of this Jacobian of gradients can't be any more than the parametric dimension minus this dimension of the space of global symmetries. Okay. Questions about that? But then that's still, you wonder whether there are symmetries that are more local. And in fact, we kind of see that there are, based on those plots, or at least there's some kind of hint that there are. But it's really unknown what they look like in general. So let me just tell you one source of local symmetries. And maybe I already did this, but let me just go ahead. So this is what I call stably active and stably inactive neurons. So for this, I sort of have to tell, well, I don't have to, but I will tell you a little bit more, which I think is also kind of an interesting perspective on understanding this whole theory. So here I've drawn the neurons of a 2-3-3-1 architecture. And I'm going to draw some additional neurons up here, kind of fake neurons up here, which I'm going to call the bias neurons, bias nodes. So these are the input nodes. These are the components of your input vector. Maybe I'll make them in a different color too. This is your output node. So you may have, we may know the following claim. I may have said it before. Repeat it, I did. That's the class of value neural network functions of any architecture. Is piecewise polynomial. And the inputs and the input coordinates and parameter coordinates. And really the best way of understanding that is to look at this computational graph. So and then I have these sort of special nodes up here. And each edge on this graph is weighted by a parameter. So this is kind of a graphical way of representing the affine linear transformations that you have for each layer map. Okay, so for example, this edge right here is part of the first weight matrix, and it's in the third row in the second column. And here, it's the second weight matrix, third row, third column. Third weight matrix, first row, third column. And I'm designating these bias nodes as special, just to keep them kind of separate from what you call the architecture. But the point is that that these also have edges coming out of them, and those edges are labeled by the biases. So this edge, for example, would be the bias associated to the first layer map, the third output neuron. And now if you put numbers in these input nodes, or if you designate them by formal variables, which are the coordinates of the input space, and here you always put 1. Then you can construct the polynomial for a linear map, for a linear neural network, by just writing down the sums of the monomials in the weights and biases that you get by taking complete paths from input or bias nodes to the output node. Okay, so for any complete path, for example, this one, you have a corresponding monomial in the input coordinates and the parameters. From this node, you have, say, this path. So here's 2 examples of paths. So 2 monomials associated to paths. For example, X2, W132, W233, W333. And then there's this one from this bias node. So that's B31, W332, B313. So here are 2 different monomials corresponding to paths in this computational graph. So I'm not even going to call this a proof. I'll just say why. maybe it's not even fair to call it a proposition, but the point is that, I'll start by talking about linear networks. So if there's no activation, neural networks with no activation, we're calling linear networks. So the polynomial, it's actually not piecewise polynomial, but polynomial. Polynomial in the parameters is given by, well, if it's called gamma I, the paths originating at I, originating at input node I. And to the output node. And let's call gamma, say star, paths originating at the bias nodes. And so I don't want to erase this, so I'm just going to write it down here. So the polynomial, the sort of formal polynomial in the parameters theta and the inputs x, in this case will just be the sum over paths in gamma I. Sum over I equals 1 to n0. Xi, and then I guess I was calling the monomial. But let me use the notation I did. Monomial associated to, sorry, gamma in monomial associated to gamma, which includes the input. I think I didn't want that actually. So sorry, because I'm going to be coming back to this later. For my monomials, I'm not going to include the input. I'm just going to include the edges on the path. So I'll put the input here. And then plus the monomials associated to the bias nodes. So this is for just a linear network. Now, what's different about ReLU? Well, sometimes neurons are off. That's the only thing that's different about ReLU. And that's actually why it's such a nice activation function computationally, because it really, basically what you have is this picture, but sometimes neurons are off for points. Okay, so for ReLU, value. Neuron I layer L said to be inactive, respectively active. The sign, if it's pre-activation sign, and this is my notation for the pre-activation output of the ith neuron of the alpha layer, is greater, less than or equal to 0, respectively greater than 0. So active if it's greater than 0, inactive if it's less than or equal to 0. And it's said to be stably inactive, active, respectively. If you actually have a negative or positive sign. So the sort of very easy point here, the sort of beautiful picture, and the reason why ReLU works so well, is that if a neuron is inactive, then paths through it disappear, and the corresponding monomials disappear. That's the whole beauty of ReLU. So say a path gamma is said to be open at a point X in the domain or a parameter theta. If there are no inactive nodes along it. If all neurons visited along the path. So if for some reason, say, this neuron is inactive, then all of the monomials that go through it disappear. Okay. So then let's now I can kind of just introduce a little bit, just a tiny bit more notation. Then X in the domain, theta not number. We could let gamma X I be open paths for X originating at the ith input node. You can let gamma star X be open paths for X originating at the bias node, at a bias node. And then the polynomial. So. Yeah, the polynomial at least at x, a polynomial at x that computes, that is the same as the function there, is looks very similar. The only difference is that you're just counting open paths. I mean, say more about this when we actually end up needing it, but what you may be starting to notice actually is that at least for most points x, this polynomial is valid in an open neighborhood of x and theta naught. So so you could actually think of this as being a formal polynomial that's valid for all points. So valid for representing the function for all points nearby. And that will actually be important for us next time. But for now, let's just think of this as like, okay, this is a way that you can compute the value of the function at x for theta naught. Okay. All right, and then the reason why I wanted to say this is that this changes the local space of symmetries. This could change the space of local symmetries. So now this gets at a kind of third notion of symmetry, which I'll state now. So I talked about global parameter space symmetries. I talked about local parameter space symmetries, although I haven't quite given any definition of local parameter space symmetries. But in lieu of doing that, I'll talk about local data dependent symmetries, because this is sort of more what we're talking about when we're talking about, say, something like a batch functional dimension. So here's the definition. Let me match my notation from before. Local data dependent symmetry of parameter space, well, of a parameterized function class. Symmetry of F near theta naught in a parameter space on a batch Z of points in Rn0 is the action of a semigroup. So again, it's a map, it's a representation of a group, of a semigroup, sorry, into smooth maps from the parameter space to itself. Oh, actually, sorry, no, because it's local. We want it just to so we only need it to act on some epsilon ball around theta naught. So some epsilon greater than 0. such that for all elements of the semigroup, for all X in the batch, and for all theta in this epsilon neighborhood of theta naught, the function agrees. And the point here is that if you have a batch of points for which any neurons are stably active or stably inactive on that batch, on the whole batch, then the space of symmetries, then the sort of effective parameter space and the corresponding space of symmetries on that effective parameter space is altered. So let me just put it this way. Here's the proposition. There are neurons that are either stably active or inactive on a batch. Then the architecture behaves like a different architecture. So let me set the functional dimension upper bound coming from global parameter space symmetries. Known global parameter space symmetries corresponding to conjugation by elements of the general linear group. Subgroups of the general linear group. The various layers are altered. So this, I'm not stating this proposition formally, but just as an example, closure architecture looks like this. And suppose that on your batch, so I'm gonna make the stably active neurons yellow. So these ones are stably active. On the batch C. Okay. And then maybe you have just one stably inactive neuron. Maybe it's here. Then the point is that you can pretend like this stably inactive neuron just doesn't exist. So it's a different architecture now. And for the stably active ones, you can conjugate by any element of the general linear group and not just the positive diagonal matrices. So you have a much larger space of symmetries there locally. And the reason why it's local is because if you move your parameter theta too much, then you might move a bent hyperplane across one of your points. And then stable activity or stable inactivity might change. So that's why it's local and not global. Okay. So let me just end it there, and I'll pick up with some slightly different stuff next week.